Good morning, everyone. So today's lecture will be on stereo reconstruction. So last week we discussed projective geometry, right? And we learned about vanishing lines, vanishing points, cross ratio, and then we use these projective invariants to measure height of an object, right? Given a reference height, we measure the height of an object. So if you remember from last week's lecture, the aim was to recover geometry from a single image, right? So in this lecture, we will actually introduce another camera, right? And instead of single image, we'll try to extract some information from two cameras, right? And we'll see that that's really helpful. Now, this process is called stereo vision. When you introduce a new camera and you try to capture a scene with two cameras, that's called stereo vision, and we'll try to understand that concept today. We'll also understand epipolar geometry. We'll discuss some epipolar lines, epipoles, epipolar planes, and all that stuff. And we'll also discuss how to calculate the essential and fundamental matrices. And we discussed image rectification in the last lecture. We'll also discuss that for stereo vision case. So we'll have a stereo image rectification, and then we'll use all these concepts for 3D reconstruction using stereo cameras, using two cameras, and then 3D reconstruction using structure light. So let's assume you captured this image using a camera. What you see is just a point, a dot, right? Now, looking at this image, can you tell me how far this image is or was from the camera or from the image plane? No. So there is always a depth ambiguity in single image. And this depth ambiguity has something to do with the scale of the object. We'll discuss that in the next few slides as well. So let's assume, keeping this image in mind, let's assume there are multiple points on array OP. And if you take projection of one of these points, you can't actually tell which point you're projecting if only a single image or one camera is available there, right? And keeping the concepts of projective geometry, the expression for x and y, that is the image plane coordinates, will be given by these two expressions, right? F of f times x divided by z. These are just the projection of your real world 3D points on the image plane. Now, if you look at this factor k on the right hand side, what does it mean? So if you multiply your x, y, and z by k, the values will change by the same proportion, right? Your x, y, and z are changing by the same proportion. So for example, if your k is equal to 1, you will get this point. You multiply your x, y, and z by 2, let's say, you get the next point. So k is not changing your overall proportion between the points, right? So x, y, and z stay the same. You're just multiplying by the same factor, right? So just think of k as k equal to 1, you get this point. K equal to 2 take you to this point, right? K equal to 3 gives you k times 3, k times y, k times z, right? So all the three coordinate values are changed by the same factor, right? So let's say you take projection of these points on your image plane. From your single image, you can't really tell which point has been projected on the plane, right? And you don't actually know the distance of or the depth of this point from your image plane, or the distance from a camera. Now, to resolve this ambiguity, what can we do? There is a depth ambiguity, right? You can't tell the distance of the point from a plane, right? Because the only information that you have is this image, right? Just this image with the point on it. Stereo vision. introducing another camera, right? And the stereo vision system actually resembles our vision system. We have two eyes, right? We have two eyes. So that is, and what happens? Your image is actually formed on one retina, on the right retina, on the left retina, right? And that actually helps you to understand that image or understand the disparity between your left and right retina, right? So the disparity between your left and right retina image gives you a perception of depth, right? So your image is formed on your left eye, an image is formed on your right eye, and that actually helps you to, that gives you the depth perception, right? And this disparity in images is proportional to the object's distance. To explain you that, let me just give you an example. So you just hold your thumb in front of your face. You close your left eye or a right eye and look at your thumb, right? And then you switch between the eyes. And you will notice that your thumb is moving with respect to the background. That's basically disparity, right? Now, if you look at the moon and you close your left eye and then you open your left eye and close your right eye, will you see any shifting? No. Just try that. And what's the reason? Distance. Because moon is at a far off distance, while your thumb is very closer to you, right? And I will support this statement with a mathematical proof in the next couple of slides. And just keep this statement in mind: disparity in image is proportional to the object's distance. So if an object is closer to you, there will be more disparity, and if the object is far away from you, there will be less disparity. Now, what happens in 3D movies? Two videos are captured in a similar way, but they have horizontally polarized lens and they have vertically polarized lens. So an image is formed on one lens, an image is formed on another one, and all the processing is actually done in your brain. They're not doing any 3D processing for the 3D videos, right? It's just the acquisition system that creates this disparity. So all the processing is being done in your brain, all that 3D perception, all that stuff, right? And I'm not sure, have you seen those glasses which has green and a red lens on them? They're made up of some cardboard sort of stuff, and they're normally used for 3D videos as well. They call it 3D glasses, I think. And you can find them in with some video games or DVDs as well. Right? So what happens there with your green glass, you see the green color, with your red glass, you see the red color, and that actually gives you some depth perception, right? That actually, so you just see different colors with different glasses, and that gives you basically a 3D effect in that particular case, right? Now, to generate that 3D effect or this depth effect, we have random dot stereogram. So you generate an image with random dots, right? So you just take, and this random dots or this image is just a matrix. You can generate this matrix in MATLAB using some random values, right? And if you look at that, is zeros and one, combinations of zeros and ones. So just random dots, and you select a rectangular region inside this image, and you move this image. Let's say you move this rectangular region to, let's say, left, right? And you fill that space. You fill that space. Although this movement is horizontal, but if you look at this image, the rectangular region, this region here, will appear in either in front or behind the rest of this surface given in this image. So it also gives you some sort of 3D effect, some depth sort of perception. What you have done is you have this rectangle, you have just moved it to the left, and you fill this space with random dots. If you look at this part of the image, it will give you an impression like it's either in front of or behind this square surface. You can try that in MATLAB. Right? It's just normal random generation of numbers, a rectangle, shift it, and fill the rest of this part with again some random numbers. Okay, and if you look at that image, it will give you some depth sort of perception, right? Now, another way to generate the similar effect is to use color coding, right? So you use green and red color. Then you have a window here, a square window. You slightly shift that window, and you fill rest of the portion of that window with red color. So here your green indicates shifted image, and red indicates non-shifted image, right? So you can try different color values. So just try green and red, combination of red and green, and as you shift your window, just fill rest of the image with green pixels, and that will also give you some depth perception. You can use color coding and view with colored 3D glasses. Of course, you'll need colored 3D glasses because all your green pixels will be, you'll be able to see all the green pixels with your green glass and the red one with the red one. That will give you some sort of 3D effect or the depth sort of information in that particular image, right? So these are just brief concepts. We're still not there. We have not introduced another camera in the scene, right? We are just discussing, okay, how to visualize the depth. How can actually you introduce these sort of things using just one image? But we have not introduced our second camera yet, right? So we are getting there slowly, right? So now this random dot auto stereogram was invented by Christopher in 1979, and these 3D images were very popular back in 80s, right? So what they did, they used a single image to create a 3D effect, similar way that we have discussed. So random dots, you move some object, and that gives you a depth sort of perception. I'm not sure, have you guys seen these sort of posters or not? You shift them a bit, and it gives you a depth sort of information. Okay, although it's just a 2D image, but the way information is represented there, it gives you the depth perception, right? So the human mind is excellent at resolving stereo image disparity to perceive depth, and does not even need to interpret the image to do so, right? We already know. You look at an image, you can easily say, okay, this is a round bottle, and you can tell about the depth of this as well. You can also tell about this one, okay, this one is this much deep or something, right? So your brain automatically processes all these things because our system is already intelligent, it's well trained. But what is our aim here in computer vision? Can we make a computer do the same? Right? We are not here to train our brain, we are here to train the computer. We are here to give this capability to the computer, right? As a computer vision researcher or as a computer scientist, if you're working in the area of computer vision, so what is the aim? Give this capability to the computers, right? So let's say if you think about your project, the face recognition project. I think this face recognition task is very trivial for you guys. If I show you 10 images and I bring an unknown image, you can easily tell me, okay, this image belongs to person number 1 or person number 2, right? But you're giving this capability to your computers, right, by writing your own program in your project, so that your computer should give you the same recognition performance as we have, right? So that's something you guys are already doing, okay? So, yeah. So now, coming back to the main problem. So given single image, we have depth ambiguity. We have depth ambiguity there. Now, to get rid of this depth ambiguity, what we normally do is we introduce another camera here. And these stereo cameras can actually resolve this ambiguity, the depth ambiguity problem. All right? And if you notice in the image, look at the second image plane, you see a line, and all the points have been projected on a line. Now, let's say if this projection is from this point, looking at the second image, you can easily tell, okay, the point is right here. This point is this far from the image, right? And a single word point P and two opticals. Okay, that's form a triangle. We'll discuss that in the next few slides when we'll discuss epipolar planes. And we can find the location of P in world coordinates using that triangulation. Again, that's we'll discuss that in the next few slides. And what was there? Okay, so given your optical centers of your cameras, you already know the optical centers. You have left camera, you have right camera. You already know your intrinsic and extrinsic parameters. You already know the optical centers. Given those optical centers in world coordinates, so camera calibration, let's say we want to find the world coordinate at pixel P. So you already know, okay, you have projection here, and you have projection of all this point here on a line, right? So instead of searching for the whole image, you have reduced your search to a line only. You already know you have a point here. You already know the coordinates of this point, right? You can click here and find the coordinates on this image plane. But you have no information where this point is in this particular image. You have to search for this point. And instead of searching for in the whole image, you are reducing your search just to one line, right? Any questions here? And this line is basically this ray, right? So, in other words, we want to find the location of P inverse. Since P in its projection on the left image plane, to complete the triangle, we need to find the projection of P on the right image plane. On the right image plane, what will you get? A line. So point on this image plane corresponds to a line on this image plane, right? And why a line here? Because we are reducing search to this line here, and that's just the projection of this ray here on this image. Right? It's clear? Okay, now this is called finding the corresponding point of P. How do you find a correspondence? Or the correspondence problem. So as a problem, it doesn't have mathematical solution. You'll have to go with something like template matching and all that stuff. Now the question is, you have this point here, you have projection of this ray here. How do you find correspondence? You already know this point, right? How will you find a corresponding point here on this line? So this point corresponds to this line. We know that. So we'll only search for this point on this line. But how will you find a corresponding point? So let's say if you're projecting this point and you say, okay, corresponding point is here, you'll get an error.
You have to know the relative positions of the two origins.
And that you already know. That's the extrinsic parameters of your cameras. Mm-hmm. Through geometry. So if you
know the distance between the two origins and what angles they're at, then you can work out what point is or which line is this.
So no, we are not measuring the distance between the points. What we are trying to figure out is which point we have projected here actually on this image. We don't know. So we have 5 different points, and if you project all of them, they all will project to a single point in an image, and that depth ambiguity will be there, right? And the solution that you get, yeah, that may be possible, yeah. In fact, if you think about some sort of cross ratios, yes, cross ratio can help you. What else? Template matching. You extract a template around this image, similar templates here, and match them, right? Other thing, let's say, to solve this correspondence problem, you have this point, you take it as a center, you take a square, a window around it, let's say 3 by 3 window, or 5 by 5 window, or 7 by 7 window around this point. You compute, let's say, hawk features or surf features, right? And you take the same size window around one of these 5 points, and you compute 5 different hawk or surf features, right? So let's say you have computed surf feature for this image plane, you compute 5 surf features for this image plane, and you match all the features, right? The corresponding points will give you minimum error. The matching will give you different, like say you are computing distances between those feature vectors. So given this one, you compare this feature with this feature with that one, this feature with the third one, fourth one, and fifth one. So you will have, let's say you're computing Euclidean distance between them or some error measure. And you get 5 different error values or 5 different distance values, right? So the minimum distance will actually give you the corresponding point in the other image plane. That's how we do it in computer vision, right? Well, while extracting features and while finding correspondences between points. Whether it's 2D or 3D, procedure is the same, right? So we have a correspondence problem which could be solved with the way I have explained you guys. You can find the corresponding points. Now, there are 2 tasks you need to take care of. For each point in the left image, you need to find a corresponding point in the right image. You already now know the procedure, right? So you take a square window, compute some features, and match those features. And the feature with the minimum distance will help you to identify that corresponding point. And the next step is calculate the 3D XYZ coordinate of point P. All right, so 2 tasks, finding correspondence and finding 3D coordinates. Any questions so far? It's clear? So let's discuss a simple stereo vision system. So given 2 cameras, we rotate the cameras in such a way they are along the x-axis, and to keep it simple, we are just taking translation along the x-axis. So this camera has been shifted by tx, right? And you don't care about the x and y at the moment, so it's only translation again along your x-axis, right? Keeping the previous expressions for x and y, the projected values of your real world point on the left image is given by f of x by z, and y of l equal to f times y divided by z. Now given that we only have this translation, now just move your right camera and project its points on the left image, the way it has been done here. So just move your right camera and project all the points on the left image plane. Now you already know the translation. It has been done. It has to do something with the extrinsic camera parameters. External world, you already know that rotation and translation because you do it yourself. It's not intrinsic, right? So you already know this translation, some distance value or whatever, and you project these points, and if you compute the expression of your x and y on the right hand image plane or the right camera, they will be given by x minus tx divided by z. So that tx, that translation will be subtracted, and that will give you an equation for the point on the right image. Okay? Now, with these expressions, let's move to stereo disparity. Any question on this one? So you have translation, you move the camera and project the point back on the left image plane. You align the camera with the right camera with the left camera, right? And just project your point, and this gives you this particular equation. You already know the translation tx. Now, with all these expressions, you already know your xr, xl, yr, and yl. Now, as we have assumed our translation along x-axis, right? Our disparity will be between xr and xl values, and that can be computed using this particular equation, which is given here, is stereo disparity d equal to xl minus xr. What is this equation, xl minus xr? For example, you have a point 2, 7 and 6, 7. So xr minus xl will be 6 minus 2. So disparity will be 4 pixels, 4 pixel values. Now this projection is on the image plane, so we are talking in terms of pixels, right? So XL minus XR will be your just X value. So coordinate value 2, 7, let's say, and 6, 7, and 6 minus 2 will give you 4 pixel disparity. Now, if you substitute the values and solve this equation, you get D equal to F times Tx divided by Z. You already know Tx and focal length. And you already know disparity, which is given by D equal to X minus XL minus XR. You already know that value. Let's say it's a 4 pixel disparity value. And we are interested in finding the depth. Right? Depth is our aim. So depth is given by Z equal to F times Tx divided by D. Now if you look at this particular expression, depth is inversely proportional to disparity. And that's what we discussed at the beginning of this lecture. So an object that's close to you has what? Keeping this relationship in mind. So these two are inversely proportional, right? Okay, so far off object will have lesser disparity and a closer object will have more disparity. So note that the depth and stereo disparity are inversely proportional, and I've said this expression, this mathematical expression is supporting that statement as well, right? Excuse me. Now some important terminologies before we move forward. So epipolar geometry, so we have a 3D point P and two optical centers OL and OR define an epipolar plane. So we talked about a triangle, right? So that triangle is right here. So your point 3D point P and your two optical centers define this triangle, and this triangle is called epipolar plane. And now the intersection of the epipolar plane with the image planes define your epipolar lines, which is right here. So that's intersection of your image plane with your epipolar image plane with the epipolar plane that defines your epipolar line. And a epipolar line and image plane intersects as epipoles. So your epipolar line will always pass through epipoles, or your epipole will always lie on your epipolar line. So if you take the dot product of the two, what should you get? Dot product of epipolar line and epipole should be equal to, it's a line and a point. The intersection here, if there are two lines, you take their cross product, that will give you intersection. But if you have a line that passes through a point and you take the dot product of that point with that line, what will you get? 0. So that product should give you 0, right? And epipolar line is the image in one camera of the ray through the optical center and image point in the other camera. It's the same concept that we discussed here. So point in one image plane corresponds to a line to another image plane. And epipole is the image of one camera in the other. We will discuss that more in detail in the upcoming slides when we use these concepts for calculating essential matrices and fundamental matrices, and that will clarify all these terminologies more in detail. Now, the essential matrix and the fundamental matrix, they both are 3 times 3 matrices that encode the epipolar geometry of the two views, right? Multiplying a point in one image by the essential fundamental matrix gives us the epipolar line in the second image to search along. So you can think of these matrices as the matrices that project your real world information on your camera plane. If you remember your camera calibration and projective geometry lectures, there was one matrix that has rotation, translation, all those parameters, and that actually mapped all your real world information on the camera plane information. So these matrices do the same for you, right? But again, it's a stereo vision concept in that terminology. So it doesn't give the exact location of the point. We need to search for the exact location using template matching, for example. So again, you need to find the correspondence. And for correspondence, what do? Again, as I've explained, you can do template matching. You can take a fixed size window again around each point, compute some sort of features, match those features, and that will give you correspondence between the 2 points in the image plane and 2 different image planes. And that has again to do something with that correspondence problem. The search for the matching point is constrained to the epipolar line, and this is known as epipolar constraint, as I've told you here in this slide. So what do? You take projection here. So this point corresponds to a line in this image, right? So what you're doing is you're reducing, you already know this point, right? Just a click and that will give you the coordinate of this point. But here you don't know where this point lies on this ray, so you're just reducing your search to one line. Instead of searching for the whole image, going from starting at this point and going all the way to this last pixel, instead of doing that, you're restricting yourself, your research to this line, this horizontal line, right? There won't be many points there. Let's say if this is 10 by 10 image, 10 by 10 image, so you're just going through 10 points, right? Instead of going through 100 points, because they're 10 by 10, so right? Okay. So how to compute this essential matrix? So that involves, the first relationship is involves your rotation and translation, your extrinsic matrix parameters. So your essential matrix deals with extrinsic parameters of your camera, right? Just keep this statement in mind. And when you talk about extrinsic parameters, what do those parameters involve? Rotation and translation. And you already know that rotation and translation here is given by R and T. And this is the standard expression that's used for computing the rotation and translation between 2 rays or 2 points. Right? You subtract the translation and you multiply by the rotation. That is standard procedure. Whether it's 2D or 3D, the same procedure is used. Now, this first expression can also be written as PR transpose R times S PL equal to 0, where matrix X is given by this. This T is basically a vector, right? It's basically a vector, 3 times 1 vector or 2 times y vector. What you need to, but here we have it's a 3 times 1 vector because the X, Y, and Z. We're talking about depth now. And just to get rid of that minus sign, you can write your matrix, your vector T in this form, in the matrix form. And S is just a matrix representation of your vector T. Okay? It's just the matrix representation of your vector T. And we are writing it in this form just to get rid of that minus sign and minus T from that expression. So using this matrix representation of your vector T, this expression can be written as PR transpose times RS times PL, which is equal to 0, and then PR transpose EPL equal to 0, and E equal to RS gives us our essential matrix, right? R times S is the essential matrix. That's the mathematical expression for the essential matrix, right? So the important thing is just keep in mind, essential matrix deals with the extrinsic parameters of the camera, and just keep this expression in your mind, right? It just deals with the rotation and translation, extrinsic parameters of the camera. And the essential matrix has rank 2 and depends only on the extrinsic parameters that I have been telling you again and again, right? So just these are just few mathematical steps to derive your expression for your essential matrix. Any questions on this? Any questions? Yep. PL is the line and the projection of the line there, and PR is also a line there, right? And again, yes, you have one point projected on one image plane, other one projected on image plane, and you need to find the rotation and translation between those points because again they are on different planes. You don't know the relationship between them. But yes, as rotation and translation are the extrinsic parameters, using those parameters you can find that relationship. Okay, now this equation PR transpose EPL is called Longuet-Higgins equation, And as I've told you, this equation actually relates to points, but by substituting these values in the same equation, you can actually derive the relationship between the image planes. So this Longuet-Higgins equation gives you relationship between two rays and relationship between 2 points, right? The same expression you already know that we have done XL equal to F divided by Z and all that thing. So the same expressions are there. You just substitute those expressions of the ray for the ray in this equation, and you get the relationship between 2D points. So this equation gives you expression for two rays in world coordinates and points in the world coordinates, right? So just if you look at it, we have capital P for the rays and small p for the points. Just keep these terminologies in your mind for the rest of this lecture. So, talking briefly about this equation, this Longuet-Higgins equation, it says that an image point can also be thought of as a viewing ray. So UV is your 2D image point. And if you define this equation, UVF will give you 3D point in your image plane, and KUVF will give you viewing ray into the scene, and KXYZ ray through the point P in the scene. So these are the terminologies that have been defined in this equation, and these were used to draw all these equations which I shared in the previous slide. So K again will be given by F by Z, U will be given by F times X by Z, and V will be given by Fy by Z. If you remember the expression for XL and YL, so that U and V is the same thing, but it's now in the pixel coordinates on the image plane, right? The problem with the stereo vision is that it needs intensive mathematics. You can't actually explain it without that. So there will be a bit more maths in the upcoming slide as well, but the problem is that you can't explain it without it. So, but again, yes, if you go through these slides and these lectures a couple of times, these will start making sense. You will clearly start to understand that, right? So these are some basic mathematical relationships, and trust me, they're not difficult to understand, right? Now coming to defining the epipolar lines. Now consider the line L, A, B, C in an image, and you know that the line can be written as AU plus PV plus C equal to 0. Now you consider a point P equal to UVI in homogeneous coordinates. I hope all of you remember the homogeneous coordinates from the previous lecture. You have X and Y value, and the last value represents the scale. And when you convert back to in homogeneous coordinates, what do? You just divide by the last value to get your actual X, Y, or U, V values. Now recall that if P lies on line L, then the dot product will be equal to 0. The dot product of the point with that line will be equal to 0. And I hope you guys still remember the expression PR transpose times T e raised to the power PL equal to 0, right? It was right here, the first expression from the Longuet-Higgins equation. So to make this product equal to 0, keeping this definition, if a point lies on a line, their dot product is 0. Now to make this product equal to 0, if this is the given point, E times PL should be your line, right? So if a point lies on a line, right, on a line, and you take the dot product, what happens? You get 0. And from Longuet-Higgins equation, we have this expression. We already know these are 2 points which are related by the essential matrix. But to make this dot product equal to 0, you can think of these two values as your, this product gives you a line, right? So a point, the dot product of line with this point will give you 0. So the epipolar line is given by LR equal to essential matrix times your point on the left image plane, right? And it corresponds to the point PR, and the point on the right image plane. And I've told you, point on one image plane corresponds to a line on the other image plane, and a line on one image plane corresponds to a point on the other image plane, right? So similarly, the epipolar line on the left image plane will be given by LL equal to E times transpose PR, which corresponds to the point PL, point on the left image plane. Now, a point in the right image corresponds to a line in the left image plane, a point in the left image corresponds to a line in the right image plane. Again, keep the first initial few slides in your mind where we have two cameras, and you have a ray of light with multiple points on that. You take the projection of the point, and you take projection onto the plane, that gives you a line. So projection of one point corresponds to projection of line on the other image plane. Any question on this one so far? So epipoles lie on epipolar lines, as I've been telling you guys telling you guys this. So we have expression here for epipoles that relates to your point with epipoles using an essential matrix. You just need to keep this expression in your mind. And in fact, all epipolar lines contain the epipoles since they intersect at the epipole. If you remember the definition from the slides where we define epipolar lines, epipoles, and all that stuff. Now notice that E has right and left null matrix, a null vector. You have a left and right null vector. That's why your product of essential matrix with your epipole gives you 0. All right. So E has left and right null vector. Just keep this property of essential matrix in your mind, right? And these two null vectors are the epipoles in this particular case, right? So the two null vectors of essential matrix give you your epipoles. Any question on essential matrix so far? So essential matrix is equal to R times S. S is your translation matrix, which is again representation of your translation vector. Rotation is again a rotation matrix. You already know that, 3 times 3 matrix. And the essential matrix has to do something with your extrinsic camera parameters, right? And it has two null vectors that represent your epipoles. Some basic things that you need to keep in mind, right? Now, the essential matrix uses camera coordinates, extrinsic parameters, right? We want to perform computation in pixel or image coordinates. That's our aim, of course. For image processing, you need information in the image plane. And if only possible if we know the intrinsic camera parameters, and the fundamental matrix actually helps you to achieve this. The fundamental matrix is similar to the essential matrix because it gives the relationship between points and epipolar lines and image coordinates. So instead of camera coordinates, now you have a fundamental matrix that gives you all the information, in the image coordinates, right? In terms of pixels, not in terms of real world coordinates, right? So the pixel coordinates and camera coordinates are related by an affine transformation matrix. So given these particular expressions, ML and MR actually here represent your affine transformation. You substitute all these values in the equation for the essential matrix, PR transpose E times PL. And when you solve these expressions, this expression here, if you look at F, is defined by your affine transformation for your right and left image planes, and the product of the essential matrix, right? It's just a normal substitution, affine relationship of your affine transformation, right? Again, transform your real world information to image plane information. That's what that matrix ML is doing. And if you remember, we defined some, we briefly discussed this affine transformation in the last lecture. And we discussed some of the property that are preserved during this affine transformation. It has to do something with the shear ratio and distortion, right? If you substitute all these values in your third equation and solve it, the final equation will give you the value of F. And that's what we are interested in. You just need to keep this expression in mind. F is given by this particular product. And that defines your fundamental matrix, and again it deals with all the intrinsic parameters of your cameras, like affine transformations and all that. Now again, F is a rank 2 matrix, and now it depends on extrinsic and intrinsic camera parameters, and thus all previous, so all the derivations or explanation that we have used to explain fundamental matrix, they all can also be used, they're all also valid, equally valid for your essential fundamental matrix as well, right? So everything that we discussed for the essential matrix, they are equally valid for your fundamental matrix as well. So I hope you guys remember this expression from your essential matrix. So essential matrix times your epipole is equal to 0. Similarly, fundamental matrix times your epipole is also equal to 0. So again, same relationships hold for your fundamental matrix and your essential matrix. Now again, keeping that projective geometry concepts in mind, you're taking projection on the image plane, and this matrix is just helping you, right? This matrix is helping to transform your information from the real world to the image plane. And if you talk about the pixel relationship, we have this expression at the bottom for the left image, image that is formed on the left image plane, on the right image plane. So U, V are the pixel coordinate values on the right and left image plane, and they are related by this particular expression. Now, estimating the fundamental matrix using this pixel information in your mind, you have a vector comprising of the pixel values from your, let's say, left image plane. You have fundamental matrix F given by the expression with the center matrix, and then you have another vector that contains pixel information from your other image plane, right? And if you just multiply these matrices and write them in the form of linear equation, you will just get this right, this bottom equation, right? That's just one linear equation. And one set of corresponding points give you one equation, of course. So we have one x, y, z point that will give you one equation of the line, or this one linear equation. And what are the unknowns? What are the unknowns here in this equation? Okay, so this linear equation, you can write it in this form. Now, if you look at these two vectors, where are the unknowns? What are we estimating? Yeah, so what is unknown here? Which vector is unknown? It's right vectors. We don't know these values yet, right? So we are estimating the fundamental matrix. That's the ultimate aim. Now coming to these points, these are your pixel coordinates. You can find them. Let's say you have 8 different points. You just click on those points, and you get information about the x, y, z coordinates, right? X, y coordinates actually, because you have image plane. It's a 2D image. Now, to estimate this matrix, what you need minimum 8 points. You need minimum 8 points. And if you look at this linear system of equation, you have Ax equal to 0 and A has rank 8 in this particular case. How many unknowns are there now? Sorry, how many values are here on your left matrix? If you look at Ax equal to 0, how many values are there? 9 values, right? 9 values. So you need minimum 8 points for estimating your fundamental matrix. But of course, the more the better, because your clicks are not accurate, right? So if you have more points, that will help you to estimate this fundamental matrix easily or accurately. Okay. Now to solve this problem, to estimate that, we have an 8-point algorithm, right? So you construct your M times 9 matrix A. So in terms of previous example, what will be M? M is, if you have 8 points, M by 9 matrix will be? What will be the size of M by 9 matrix? So this is your matrix A. So you construct a matrix A, M by 9. So you already know there are 9 values here. This matrix has 9 columns here, right? So M times 9 means it's an 8-point algorithm. And if you have 8 points, What will be the size of matrix A? 8 times 9. Right? You construct your M times 9 matrix. Right? So you have 9 columns there. And you have 8 points. You'll get 8 by 9 matrix here. So A will be an 8 by 9 matrix. You construct your M by 9 matrix. And you find singular value decomposition of A. That will give you this particular expression. Again, if you remember from, it was that object recognition lecture or feature extraction where we discussed PCA. I think it was object recognition. We discussed SVD and all that stuff. SVD you can compute in MATLAB using just one line statement. There's SVD built-in function in MATLAB. So you find single value decomposition that gives you the expression, this particular expression. Now the last column of U contains the entries of the F matrix. Right? So the last column of U contains entries of the F matrix. Now F must have rank 2. That's the requirement. And to ensure that, what you do, you apply SVD again on your matrix F. That gives you another set of UF, SF, and VF, right? And you set the smallest singular value in SF to 0. You force that value to 0, right? To create your SF dash, and then you recompute F using this particular expression, right? So 8 steps. That's why we call it 8-point algorithm. You construct your matrix A, you take SVD of matrix A, and the last column of your U matrix gives you your F matrix, your fundamental matrix, but the requirement is that fundamental matrix must have rank 2, right? That's the requirement. So you apply SVD again on your F matrix, you get your new values of U, S, and V. You force the smallest singular value in SF to 0, right? You force it to 0, and then you recompute F just by multiplying your U, F, and VF transpose with the new value of SFV dash, SF dash. And that gives you your fundamental matrix. Now if you look at these steps, they are pretty easy to implement in MATLAB, right? They're pretty easy to implement because you already have a built-in function SVD. And you can easily find the smallest singular value using the min command in MATLAB, and then you can set that pixel value or that element of the matrix equal to 0, right? And then just multiply the matrices, and that will give you your fundamental matrix F. And I believe MATLAB already has a calibration toolbox, a camera calibration toolbox. MATLAB already has. If you have a full version of MATLAB, it has that calibration box, and you can actually use that directly, and that will help you in computing your fundamental and essential matrices. Any question on 8-point algorithm? Is it clear to everyone? Now, this is just a general slide. So what happens, and it's not just applicable to this particular problem, but in image processing in computer vision, this is just a normal practice. You do some numerical stability where you normalize your image values, right? So in your project, you're normalizing your image values between 0 and 1, right? That's one of the ways of doing it. But what people normally do is they subtract the mean value from the actual pixel value and subtract it by, divided by the standard deviation, right? That's normalized, and that's mostly, you will find this normalization mostly in neural network architecture. That's what people normally do before giving those images to the neural network for training and testing, right? So that's one of the ways of normalizing the images. And simplified expression to do all this in one single step is using this matrix T. This matrix. So what normally people do, they take care of mean in the first step, and then they divide it by the standard deviation to normalize their values. But this matrix performs all the steps in one single. This matrix will perform everything in one single step, right? So this normalization is done using this matrix T in one step. So if you have normalized data, of course normalized using this information, and then you'll get a normalized fundamental matrix. If you're using normalized pixel information, you will get a normalized fundamental matrix. And to get your actual fundamental matrix, you just multiply your normalized fundamental matrix with T using this particular expression, and that will give you your actual fundamental matrix. So Fn is the fundamental matrix calculated from the normalized set of corresponding points. Any question on normalization? Right. It's just simple use of mean of your data and the standard deviation. Now, calculating the 3D coordinates of a point. If we have a pair of corresponding points in stereo images and we know the camera parameters of both cameras, we can find its x, y, and z location. I believe most of you are already familiar with this particular expression. We have been discussing this expression for the last weeks. So you have this matrix that takes care of the projection of your real world 3D x, y, z points on your image plane, which is S, U, and SV. And we discussed, okay, S is given by the product of your third row of your matrix with this vector x, y, and z. And then you solve for U and V using this particular expression, where this value represents your S. This one represents the product of this one times this one. And similarly, for V, you do the same expression. So we get another two equations from the second camera, and both sets of equations share the same three variables x, y, and z. So you have projection of a point on image plane as a line. You find the corresponding points using this equation. Using these matrices, you compute these equations. And if you look at these equations, this one is, of course, this one is for your, let's say, left camera. This one is for your right image plane, I would say. Right? And what is common here? These x, y, and z, because these x, y, and z values correspond to same point on two image planes. So these two are same points on two different image planes. Now both sets of equations share the same three variables x, y, and z. And these four equations and three variables x, y, and z can be solved with linear least squares. You can solve them using normal least, using the system of linear equations to find the value of x, y, and z, because you have four equations and three unknowns. So solution is possible. Do we need a break or should we keep on going? Okay. So let's move to the next topic, which is image rectification. So we did some image rectification in projective geometry, and we used homography there. I hope you guys remember homography, right? We computed matrix H, and that actually helped us to rectify an image. And of course, if you are trying to recover some specific shape from an image, rectification actually helps you in that. Now, in the perspective of, let's say, stereo vision, your aim is the image rectification actually helps you to get horizontal epipolar lines, right? So what if you have these sort of epipolar lines and you're trying to find a point here on these lines? Will that be an easy task? If you have these sort of lines, they are spreading, right? And you have your corresponding point on one of these lines. Is it easy to find a point? And just imagine it's a matrix, okay? It's just a matrix. This image is a matrix. And you have a rectified image that has horizontal lines. So finding a corresponding point will be easier here or in that case? On the right image or the left one? Just imagine you have matrix in MATLAB, and these two matrices represent two different images. One is original image, the other one is the rectified image, and you have horizontal epipolar lines, and you know that you have to search along these lines. Search on these lines. You're searching for a point on these lines. So which one will be easier? This one? How many of you for this one? This one? Yeah. Because if you have matrix, you can easily, okay, say you have, again, if you, this is a 10 by 10 matrix, let's say. You're restricting your search to a 1 times 10 vector. Instead of going through a 100 times 100 matrix, a 10 by 10 matrix, like 100 pixels, you're just going through 1 times 10 vector, right? So this one just has 10 values in it and 1 row, right? So search along the horizontal line is a bit easier, and that's why image rectification is done in stereo vision. And of course, to simplify for correspondence, because search is easier along a horizontal line. Now, this image rectification, how do you perform this image rectification? So you reproject the image planes onto a common plane parallel to a line between the optical. So let's say these are 2 regional images. You capture a scene, and then you align these 2 planes parallel to this optical center, and that of course requires a rotation around the optical center. You already know that because this is extrinsic. How much you have rotated, you already know the angle then, right? If you rotate this plane by some angle, you already know that angle, right? Because it's extrinsic. Now, a rotation around the optical center is simply a 2D homography in the image, and using that homography information, you can compute the image rectification, right? It's just simple rotation along the optical center. Now, when you rectify an image, if you remember from the previous slide, it's not straightforward. It stretches the image, right? And if you are applying image rectification in this particular case, although you're getting horizontal epipolar lines, but your image will be stretched. And what do you think? If your image is stretched too much, will you be able to find a corresponding point? Yeah, if you're stretching an image too much, you're losing so much information. There will be some blurriness in the image, right? So too much stretching of the image will also reduce the chances of finding a corresponding points. So you need a trade-off. How much to bring these lines, these epipolar lines parallel, and how much to stretch that image. Now, in this particular case, when you stretch an image, you make your epipolar lines horizontal and parallel, your epipole will be at infinity. Mathematically or theoretically, it will be at infinity. And you can represent a point at infinity using homogeneous coordinates. It's just a mathematical representation, okay? It's theoretical. And if you remember again from the homogeneous coordinates, your last value represents the scale, right? And the value here is 0. And if you divide your x and y by 0, what will you get? A point at infinity, which makes perfect sense, right? It's not 1, this is not 2, but we have 0 here. And if you divide anything by 0, that's a mathematical representation of a point at infinity, right? Using homogeneous coordinates. So you translate it back, you change this back to inhomogeneous coordinates, you divide by 0, and that will give you a point at infinity in inhomogeneous coordinates. Oh, okay, so when you stretch an image, rectified image does not remain rectangular anymore, of course, because of that image rectification. And you multiply your epipoles with the, so what is our ultimate aim? To get a point to bring the epipolar lines, to make the epipolar lines horizontal, or to rectify an image, or to stretch an image. We need an epipole at infinity, right? Now, to bring that, to take that point, that epipole to infinity, we need a homography matrix that will take care of that. Now, if you multiply your homography matrix with the epipole, you should get a point that's at infinity, which is represented by this expression. Again, this is homogeneous coordinates. So you multiply your epipole with the homography matrix, you should get 1, 0, 0 in your homogeneous coordinates, because when you use this information and translate it back to your inhomogeneous coordinates, you will get a point at infinity, right? Because you divide it by 0. Now, assuming each row of H to be a line, so H H1 transpose is a line, H2 transpose is a line, H3 transpose is a line. And you multiply each line with your epipole, or each line has epipole on it. When you multiply them, you will get this sort of expression. And in this particular expression, the first information is relevant, but the last two are relevant. Lines H2 and H3 pass through your epipole E, because we are getting 0 here, right? And it represents that they are on the infinity. And the first one is again irrelevant in this particular case. Now looking into more properties of your the homography matrix. So H is homography matrix for one image plane. H dash is homography matrix for other image plane. So we have two cameras, left image and a left camera and right camera, left image plane, right image plane. So let H and H dash be the homographies to be applied to rectify the two images. And lines H2 dash and H3 dash must pass through epipole E dash. Lines H2 and H2 dash and H3 and H3 dash are corresponding epipolar lines, and lines H3 and H3 dash define the rectifying plane. So in this particular case, if you have three lines, H3 and H3 dash from two different camera planes will define the rectifying plane in this particular case. Now remember that the pair of homography matrices are not unique. You have two different cameras. Of course, they will have two different sort of homography matrices, and you need to find the pair that minimizes image distortion. Again, it's the same thing. If you are stretching your image too much, you are introducing too much distortion in the image, and that won't help you to find a corresponding point in another line, right? So if you want to look into more details, I have provided a relevant literature there as well, a reference to a relevant literature, which is computing rectifying homographies for stereo vision. It's a technical report which was published back in 1999. So you can dig deep if you're interested. But for understanding, just keep these definition and these properties of homography matrix in your mind. Now, just again talking more about the stereo image rectification, we have just these few expressions. RL just comprises of your E1, E2, E2 epipoles, and you have these different representation of epipoles given here. Again, these are just mathematical representation, and what you need to do is, once you have these values of RL, again RL comprises of your epipoles, and once you have computed your RL vector or RL matrix for each point in your left image, let's say it's given by x, y, f, you take a product RL times P, which gives you, of course, a point that has been mapped on your image plane, and then you compute P dash, which is given by this particular expression, and then you compute your RR for the above camera using this expression called RR equal to R times RL. Now R is the rotation matrix, the extrinsic parameters. You already know that rotation and translation. So these values could be computed using, so this is just a simple, I would say, image rectification algorithm. If you know how to compute epipoles, you can simply do that in your MATLAB. So this RL comprises of your three epipole information. You multiply by the values of P, and that will give you this particular matrix. Now, this whole process of this was actually a conventional image rectification process that was previously used, right, when this stereo vision concept was introduced. But the problem with this method is it does not work when the epipoles are inside the image. Why? So when if your epipole is inside an image and you stretch it to infinity because you are trying to make your epipolar lines parallel, that will distort your image, and this method will fail. This image rectification will fail. That won't give you good results. Now, to address this problem, Paul Fees came up with a solution and he published a paper in ICCV back in 1999. I hope you guys know what is ICCV, International Conference on Computer Vision, one of the best conferences in computer vision in this area. So what he did, instead of using, he used polar coordinates in his solution, right? So he did image rectification using polar coordinates, and using that information, he stretched the lines. I have some of the results from his papers. So with the rectification, what happened, so if you look at these two images, these have been captured from two different cameras. If you can see, we have some information here, we don't have that information here, and these are basically two different images. So using the left and right image parameters and the polar coordinates, he stretched these images. He performed polar rectification, as they call it in their paper. Of course, you're interested, you can just go to that paper and look at his technique well in detail, but I'm just sharing here as an example. So if you look at this image, we have horizontal lines, and images are not that much stretched in this particular case. And if you're trying to find corresponding points in these images, they're pretty easy. So if you have a point somewhere here, if you search along this line, or where will be the corresponding line? So if you have a, let's say, point here, you search along this line, you should be able to find a corresponding point here, right? So let's say if you have another point here, you search along this line on this image, you should be able to find a corresponding point here, right? So their technique is basically just based on polar coordinates, and it's just to make sure, and it's just addressing the problem where you have epipole very close to your image plane. So what have you guys understood so far? Our main aim is to find corresponding points to get some information about the depth of a point, right? That's what we are doing. So everything we are doing here, like stretching your image, making your epipolar lines parallel, all these efforts are to find correspondence between two images, right? To forward corresponding points in two images, right? So that we get some information about that 3D point. How far is point from the image plane? How far is an object from an image plane? All that, right? So as another example, let's say we have epipoles on an image, and we have two input images, and you can see these two images are different, right? If you closely look at them, they are totally different images, especially if you look at this part of the image and the other one. So we have some camera movement there, right? A slight displacement in cameras. And if you apply image rectification here, as the epipoles were on the image or close to the camera, the images have been stretched. And if you look at this beach volleyball, shape has been distorted, right? But again, the good thing is you have some vertical epipolar lines. You can still find corresponding points on these horizontal lines, these vertical lines. So again, finding correspondences is still possible in this particular case. Now, here we have a depth map. So with two cameras, of course, we got some depth information, and you compute this depth map. Now, what happens in the depth map? You have some missing information. You have some missing pixel values that could be because of occlusion, right? And as you're using these, you're not using depth camera here, you're using normal camera, so that could be because of the illumination and several things. So what you normally do, you interpolate, you fill in those missing information, and you get this complete depth map of your input scene. Have you guys used Kinect? So this problem is very common in Kinect because you have a low resolution 3D image, and then yes, of course, after acquisition, people do some processing. They smooth the image, they fill this missing information using interpolation and all that. But again, that's all in 3D, not in 2D. Now, depth map in pixel coordinates looks something like on the left image, and if you just rotate it, you'll get some this sort of look. And yes, of course, you have some spiky data as well because of depth disparity and resolution acquisition and so many things. But again, you can always smooth this information and make it look good. And yep, if you know how to process 3D point clouds and meshes or the depth maps, that's very easy to get rid of these spikes and all that stuff. They're mostly used, they're called outliers, yes, and they are very problematic when you perform 3D object recognition or 3D face recognition because you get your features on these points as well. So what normally people do, they just get rid of them by using some processes. They smooth the images and then they interpolate and all that stuff and they get rid of it. So that's just for visualization. So that's how the image would look like in 3D. Now correspondence problem. What we have discussed so far reduces the correspondence search to the epipolar lines, and we made the epipolar lines horizontal for simplicity because search along the horizontal line is simpler, easy. But finding correspondences is still a challenging problem. What if we don't have a texture in the scene, in the two images? So lack of texture is one challenge. Repetitive texture. If you have repetitive texture, will you be able to find correspondence? So you have a fence. Fence has a repetitive texture, right? Zebra pattern, that's repetitive texture. So finding correspondence could be problematic or could be challenging in that particular case as well. Occlusion around the object boundaries. So you have two different cameras. One captures one view of the object, other camera captures other view of the object. And if there is some point which is hidden from your second camera, that occlusion could be problematic, and you'll not be able to find correspondence in the occluded area of the images. Right? Now the selection of optimal correspondence search window is difficult. So I explain you can actually take a window around your point, right? Your pixel P. It could be 3 by 3, 5 by 5, 7 by 7, and then you compute surf or hawk features and then match those features. But size of the window is again a problem. What will be the optimal size? You take a very big window, that will not be very meaningful. If you take very small, if you take very big window, you will not get very good matches in two images. If you take just very small windows, you will get multiple matches, multiple inaccurate matches. So the size of window is also very, very important. So in correspondence, these are 3-4 challenges that you also need to take care of. Right? Any questions so far? So, so we put some constraints on. There are some constraints on correspondence search. So epipolar, corresponding points must lie on corresponding epipolar lines. So if you keep these two images, this image in mind. So you have, let's say, these two corresponding epipolar lines. Then your corresponding point should be on these two lines, right? You can't have a corresponding point for, so you have a point here, you can't have a corresponding point here for that particular point. So it should be on the same epipolar line. Uniqueness. A point in one image can have only one corresponding point in the other image. That's the main property. That's the main requirement. And if you have one corresponding point, that will help you to achieve all the aims that we have been discussing in this lecture. Right? So you should have a unique corresponding point. And if you remember from, let's say, take the example of Harris corner detector. You apply Harris corner detector to one image, you apply it to the other image. You have repeatable key points, right? And that makes sure that can also help you to find corresponding points if you have repeatability there, right? Ordering. Points in the second image must appear in the same order as in the first image. That's very important, right? So if the images are, if the points are in some particular order in your image number 1, they should be in exactly the same order in your second image. And you can take care of that by the way you represent your information. Now, smoothness. Disparity values are expected to change slowly except at object boundaries. So when you get to the boundary of an image, there will be a certain change of information. You have edges there, right? So this smoothness, this disparity value will change slowly inside the image, but on the boundaries it will change suddenly. So you just keep this in your mind as well. Now, for perfecting these correspondences, you have an active stereo, which can make this correspondence search more accurate, right? Now, what is the idea behind this active stereo? The idea is to project coded light onto the scene, right? And the code determines which points correspond in the two images. And in a basic setting, we need one camera and one projector. As you are projecting light, what do you need? A camera and a projector. You can use two cameras and a projector, but I think that's not a very good approach, right? So one camera and one projector should be sufficient, and that's what most of the 3D data acquisition system do. And what is a projector? It's just the opposite of the camera, right? Isn't it? It's just the opposite of the camera. So you have optical center, and that's the point from where light emits. And then you can control the angle of the light by adjusting the lens. So it's just the opposite of the camera. So what you normally need, you need one camera and a projector, and the projector can possibly illuminate the entire scene at once or scan a line through it, right? Or we have some slides on this one. So laser stripe scanner is something that actually scans the object using a projector and a camera. You have a stripe that actually moves on the object. So let's say you're starting here. You start here and you go all the way, project that light, and the camera actually captures that stripe, right? And that gives you an X, Y, and Z information or 3D point cloud, right? So as you're moving your stripe over a camera, you will get some different variations. Of course, you have a different sort of stripe here, and if you go forward, you have a different sort of a stripe on the other on a different part of this surface, right? So this, as you move, you project this light. It's a coded light, of course. You capture this light, and it gives you X, Y, and Z coordinates, that depth information of your image. So this technology is used in all the latest scanners, right? And they project a coded light using the a laser. So I think LiDAR, they call it LiDAR or LiDAR. That's one of the ways they use to capture 3D scenes, and you will find plenty of data sets of 3D objects, metropolitan areas for different tasks. Now, a structured light system is another time-coded system. So what happens, you project different stripes of light, right? And each stripe is projected at a different time interval, and you get a different binary pattern. And that pattern actually helps you to get a 3D sort of image in the end, right? X, Y, and Z information. And I have already provided this relevant references as well for you guys. You can have a look at it if you are interested in more details for this one. But again, this is again a color-coded light stripes, and each stripe has its own information, X, Y, and Z value, and it captures X, Y, and Z value in a different way. And what happens in their technique, they have a different binary code for each stripe number, right, which is represented by these sort of patterns. So you project one line, you get some pattern, you project another one, and you get third one. That's how it works. Now, another way is to use, but of course this is This is a lengthy process because you have multiple stripes of lights. You project one light, you then project next one, you project third one, fourth one, and so on, right? So that's a bit lengthy process. So to address this one, we have color coding. So similar to the previous technique, except that the stripes are color coded. Color codes are such that they are different in the local neighborhood. So they have a different contrast. These color stripes are different contrast. And single shot acquisition of 3D. So you project these color coded lights on the object, right? And this gives you this sort of 3D image, X, Y, Z information. Just one projection, it's just one shot, right? So instead of projecting light stripes multiple times, you just project these this color coded light and you capture an image in just one shot, and that's one step acquisition. Now I found this video on one of my friend's Facebook account, and I would like to share with you guys because it gives you this actually explains you this concept very well. So you have a pattern of light, you project on an image, and that gives you a 3D image and output. So just read the captions and look at this video, and that will actually, I found it it's a good artwork, I must say. Again, they are using color coding here, right? They'll be using color coding here. And as it is on a piece of paper, it's all 2D, right? It's all 2D. But what we'll get in the end will be amazing. Again, if you look at the color combination, they're using different colors. They have a different contrast, right? And what do they get in the end? If you look at this image, it appears that it's giving you a depth perception, right? So the same concept is, they use the same concept in when they project a light. So just imagine you have a hand, you project a color coded light, and you get a 3D information, right? If this, I think this video should give you a clear idea of how that color coding actually works and how you get a 3D image from that. Okay, so getting back to the slides. Any questions so far? Okay, now we have another way of using a structured light, and that's a spatial pattern, and that is normally used in your Kinect sensors, in the latest sensors, whether it's a low resolution Kinect or the latest high resolution Kinect. So rather than color pattern, we use spatial pattern, single shot acquisition, like the color coded lights, and you can use monochrome camera and can use infrared, so it is not visible. So what happens in the case of Kinect sensor, you have an infrared light that is projected on an object, and that gives you a 3D information about that particular object. Now the good thing about the infrared light is it's not visible to us, right? And you can easily capture a 3D scene using a Kinect, right? And what do you get? It can give you depth maps. Depth map is just like a 2D image, but instead of intensity values, you have depth information. That's 3D, so X, Y, and Z. So what do you have into your 2D image? X, Y, and intensity value at a pixel. But in the case of Kinect, you have X, Y, and that you have depth information, that 3D information. Distance of the object from the camera. That's what Kinect measures. And that's what we have been trying to figure out here. Distance of a point from an image, from a camera, right? So Kinect directly takes care of that. It measures the distance of the object from your camera and translate that information in terms of depth. So that pixel information is basically depth, that's distance of your object from the camera. So you can represent that information in 3D point cloud. Yes, in our last lecture, which is on 3D shape analysis, we'll discuss how to handle the point clouds and the meshes, how to visualize them. All that stuff is covered in our last lecture. So, okay, so in this particular case, the spatial pattern is actually represented by some unique pattern, something like this. So dash is in a white circle and a blank circle. So they have their unique pattern, of course. And let me just quickly share one of the interesting works by Microsoft. I think it was by Microsoft Research. So you have a Kinect sensor, and I've told you it's just one short acquisition. So this guy is scanning an indoor scene using Kinect, and at the same time he's reconstructing the scene as well, right? So it's real-time reconstruction of a 3D scene using the Kinect sensor. And of course, as I've told you, Kinect sensor have infrared light that measures your distance of an object from the scanner. So you get X, Y, and Z information in one go. I think their code is available on OpenCL or OpenCV. I used that back in 2012. I don't remember whether it's OpenCV or OpenCL. You can connect your Kinect with your computer. Just install their libraries and just execute their code, and you should be able to get a 3D. You can scan indoor. You can scan your face. You can scan your room, and you'll get a 3D point cloud, a mesh of the scene. So real-time, I would say real-time stereo reconstruction using, or 3D reconstruction using Kinect sensor. It was very good work back in 2012, yes. Okay, now dynamic changes to the scene is another way. So when you have a change in the depth, that is also captured in real time. You change the location of an object, automatically reconstructed in the scene. And people are using this sort of information in object recognition and object segmentation. You'll find pretty good papers in ICCV, ICPR, in CVPR, in robotic conferences like ICRA and IROS. You'll find pretty good work there. So people are using these sort of 3D scenes for segmentation and object recognition. Our research group here has done plenty of work in the area, and we have some really good papers in ICRA and IROS, and we have achieved some real-time robotics performance where we use robot to identify some objects in cluttered scene, to grasp that object and put it aside. So, and all that was, yes, of course, we used a Kinect sensor in that work. So as I've said, so in the context of stereo vision, all these 3D reconstruction concepts are very important for several real-time applications, right? ICP, don't worry, we'll discuss ICP in the last lecture when we'll talk about 3D shape analysis, when we'll talk about registration and all that stuff. So that was just a brief view. Let me just see if we have something interesting coming up. Okay, it's all the same 3D reconstruction. Okay, now if you I found this one a bit interesting. If you dim the light, okay, they dim the light here. If you reduce the illumination, will that affect your 3D reconstruction? What do you think? If you have a well-illuminated scene and then you suddenly change the illumination, will that affect your 3D reconstruction if you're using Kinect or a 3D scanner? No. Why? They're using infrared light, and they're just they're trying to capture the distance of an object from a camera, right? They're actually trying to capture different sort of information. So even if you have a lesser light in the room, that won't affect your 3D object reconstruction or recognition. And that's a very big advantage of 3D. That's a very big advantage of 3D. And people are actually exploiting that a lot, and they're taking benefit of that. Okay, so coming back to the lecture. Okay, so concluding.